Hi, my name is Tristan Linscott, and for my Physics 2211 Lab 5, I chose to investigate the falling slinky. First, I will start with an introduction. The purpose of this lab is to apply physics principles and modeling techniques we have learned this semester to investigate and analyze a physical system of personal interest, which I have chosen to be the slinky. We will use tools like Tracker to gather real data, apply a physics model using GlowScript, and predict outcomes based on observations. In my model, I chose the slinky. It is at static equilibrium, and I am investigating whether or not the bottom of the stretched slinky stays stationary when dropped. This lab allows me to explore the principles of tension, gravity, and drag and their effects on motion. We can then assess whether the bottom of the computational model behaves similarly to what is observed in the given tracker video. A preview of my findings is that the bottom of the slinky will stay stationary in both the computational model and the observed tracker data, and that the position of the tracker data starts to vary after the top of the slinky reaches the bottom, likely due to human error. Now I'm going to review some main ideas and fundamental principles relevant to this experiment. First, Newton's second law and momentum principle, which states that F net is equal to the change in momentum over the change in time. This principle also helps us get our velocity and position update formulas, as seen below. Next, drag force, which is resistance caused by the motion of an object through air or any fluid, and is equal to negative b, a constant, times v squared j hat. Last is gravitational force, which is equal to negative mg j hat. Now for my observational data I gathered using Tracker and a provided video. The mass of our slinky is 0.204 grams, and for calibration, we use Derek's height, which is 1.75 meters. I gathered the initial position using the tracker data, and our initial velocity is 0 because we dropped the slinky from rest. Throughout the video, I tracked the position of the bottom of the slinky versus time. Now, for the code, I will start with initial conditions and constants we needed to establish. First is the system, which is our slinky, mass, initial position, and initial velocity, all gathered from the tracker video. Then the size of my time steps, which I also matched to the tracker video. Other needed constants are g, the gravitational constant on Earth, j hat, and b, our proportionality constant for the magnitude of drag force, which I calculated through trial and error by finding when n positions matched. The next part of the code is the loops. For the first loop, we're using the time before the top of the slinky reaches the bottom. In this loop, I calculate force of tension of the slinky, which is just opposite of gravity, the weight force, or gravitational force, and then use F net to calculate the slinky's new velocity and positions with the update formulas. I then advance the clock. In the below loop, we're using the time after the top of the slinky reaches the bottom of it. I do the same process, obtaining the ball's position throughout the loop. When comparing our results, we see that the model and observed position from the tracker follow very similar paths of position. There's no difference in the first part of the graph, as the bottom of the slinky does stay stationary until the top reaches the bottom. The positions only start to vary after this point, likely due to error in my tracker points or a calibration error. I also would like to point out what this graph is showing, which is only the position in the y direction and only the position of the bottom of the slinky. Our tracker position also likely has fluctuations due to external forces not accounted for in our computational model, but in real life. Now for additional questions. The first question I proposed was the what does it mean question. What does the stationary behavior of the bottom of the slinky tell us about how tension and gravity interact within a suspended object? My answer is that the stationary behavior of the bottom of the slinky suggests that tension within the stretched slinky counteracts the pull of gravity on the lower segments. This balance of forces keeps the bottom stationary momentarily until the tension goes away, allowing it to catch up with the rest of the slinky. The slinky, acting as a large spring, is counteracting the force of gravity with the tension force of equal and opposite magnitude. Because the forces in the y direction are equal and opposite, the slinky is in equilibrium and remains stationary. Next was the what if question. What if the slinky were dropped on a planet with a different gravitational force? Would the bottom still appear stationary, and how would the motion of the slinky change in response to different gravitational pulls? To answer this, I said that if the slinky were dropped on a planet with a different gravitational force, the stationary effect of the bottom might change. On a different planet, the tension force and gravitational force might not be equal and opposite in magnitude anymore. On a planet with weaker gravity, the bottom would likely stay stationary for a longer duration, while a planet with stronger gravity, the bottom might begin to fall sooner as the tension would need to overcome a greater gravitational pull. Thank you for watching, and bye.